Hi everyone, it's Michael. So I have a very instructive problem for you all today. This problem is from the IMO 2017 shortlist, so it wasn't on the exam, but it was number 4 out of number 8 of the shortlisted problems for geometry, so medium difficulty. So if you'd like to try to solve it, feel free to pause the video. Alright, so I'm going to go over the solution. So we have a triangle ABC, and we draw the AX circle omega. So I haven't labeled, or I haven't drawn the label omega, but this circle through GH and I is omega. So it's tangent to BC at G, it's tangent to the line AB at point H, and it's tangent to the line AC at point I. Then we draw the line BC, and we let it meet the circumcircle of AHI at points J and K. And L is the midpoint of AG, and we want to show that the circumcircle of JLK is tangent to omega, which is this X circle. Alright, so one of the things I noticed first is that the circumcircle of AHI, it has to pass through the center of omega. And that's not too hard to see, because if we let the center of omega be F, let's say, then angle FHA is 90 degrees because the X circle is tangent to AD, and angle FIA is also equal to 90 degrees for the same reason. So AHFI would have to be a cyclic quadrilateral, so I'm going to write this out. So the center F of omega, which I'm going to draw, I'll draw it right now, it has to lie on the circumcircle of AHI. That's because angle FHA is 90 degrees and angle FIA are both 90 degrees. And so the opposite angles of it add up to 180. Alright? So now, how do we get started here? We want to show the circumcircle of JLK is tangent to omega. And it's kind of tricky because we don't know where that point of tangency is. So this is one of these things that makes these problems seem pretty difficult in general. But I found a trick here that you can kind of try to use to figure out where that point of tangency is. So what we can do is first assume that they are tangent. So we're trying to prove that, but assume that they are at some point, and we don't know where that point is yet. But if that's true, then that means the radical axis of these two circles have to be the tangent line at that point. Okay? So what we could try to do is we could try to use the radical axis on this circumcircle of AJK, and then the circumcircle omega, and then the circumcircle of JLK. Okay, so if we try to use the radical axis on those three circles, what we would get is that JK, HI, and that tangent line would have to be concurrent at a point. Now we still have to prove that that line, that third radical axis is indeed a tangent line, but we'll get there. So what I'm going to first do is I'm going to intersect the two radical axes that we do know about, which are JK and HI. So I'm going to let JK and HI meet at point M. And then if the circumcircle of JLK was actually tangent, then that third radical axis, which is the tangent line to both those circles, would have to pass through point M by the radical axis theorem. Okay. So basically, that means that if I draw the tangent from point M to omega, I would want to show that that is the tangency point of those two circles. Okay? But first I'm going to notice a few things. So I'm going to bring in the theory of poles and polars here. So if some of you don't know about this, I'm going to post a link to it in the description below of the video. But it's a very useful theory. I've only mentioned it probably a couple times in my videos before, but it does come in handy, I'd say, a lot more often than I've mentioned on my channel. So I would definitely recommend learning it. But for those of you that don't know, for any point in a circle, there's a corresponding line called the polar of that point with respect to the circle. So in this case, if we take the point A and we take the circle omega, HI is the polar of A with respect to omega. And so one way to get the polar is by taking the two tangents from that point to the circle and connecting them. So from that we just know that HI has to be the polar of point A. That's not typically how the polar is defined, but I'd say that's a property of it. So the polar is actually defined this way. So we see that HI is perpendicular to AF, and if we take the distance from HI to point F, and we multiply it by the distance from A to point F, we get the radius of this X circle squared. So that's the definition of the polar, but a property of it is that if we take the two tangents from A to the X circle, then HI would have to be the polar of A. So I'm going to write this out. So since AH and AI are both tangent to omega, HI is the polar of A. And it turns out, so M lies on that line. So the polar is a line, not just a line segment. And M lies on that polar. And it turns out that there's a theorem that says if M lies on the polar of A, then A has to lie on the polar of M. So I might do a video on this later, but it's called Lahir's theorem. I don't know if I pronounced that in French perfectly accurately, but so basically Lahir's theorem says, so I'm going to write this out, but basically if M lies on HI, then A has to lie on the polar of M. So if we draw the two tangents from M to the X circle, which then the line connecting them, A would have to pass through that. So I'm going to do that right here. So I'm going to draw the line through A and point G, and I'm going to let it intersect omega at N. And then MN has to be tangent to omega because A lies on that polar line GN. Okay. So GN, like I said, has to be the polar of M with respect to omega. And so therefore MN has to be tangent to omega. So I'm going to draw that in. Okay, so basically, then we want to show that N is actually the point of tangency of the two circles in question. Because if N is the point of tangency of those two circles, then by the radical axis theorem, we'd have JK, HI, and that tangent line would concur at point M. Okay? But before I show that point N is the point of tangency of these two circles, I want to show it lies on both of them. We know N lies on omega, so I want to show that N lies on the circumcircle of JLK, which is the same as showing that JLKN is cyclic. And it turns out that this is not too hard to do using power of a point. So basically, if I wanted to do that, then I want to show that LG times GN is JG times GK. And using the information in the problem, this isn't that hard to do given that L is the midpoint of AG. So I'm gonna write this out, a little bit of algebra. But before I do that, I'm going to bring up one more thing. If we let, so I'm going to change this to point P. If we let P be the intersection of AN with the circumcircle of AHI, so if we let P be this point, then FPA has to be 90 degrees because FIA is 90 degrees. Okay? So angle FPA is equal to angle FIA, which is 90 degrees. And if you have a perpendicular from a center of a circle to a chord, it has to bisect the chord. So since angle FPA is 90 degrees, that means that GP has to equal PN. Okay. And now we can use that power of a point that I mentioned. Okay, so we want to show that LG times GN is equal to JG times GK, because that would prove that LJNK is cyclic, which is what we're going for. So LG times GN, well, we know that GP is equal to PN, so that's LG times 2GP. And then we can move the 2 out front because we want to use the fact that L is the midpoint of AG. So if we move the 2 out front, we have 2LG times GP, and 2LG is equal to AG. So this is AG times GP. And then by power of a point on the circumcircle of AHI, AG times GP is equal to JG times GK. And now we've proven what we wanted, because if we have that LG times GN is JG times GK, then that means JLKN is a cyclic quadrilateral. Alright, so that's converse of a power of a point. We know that's cyclic. And so now, basically that indirectly means that those two circles have to be tangent at N, basically by the converse of the radical axis theorem, because the 3 radical axes of JLKN, so I haven't drawn the circle, but the radical axis of that, and then these 2 other circles, the pairwise radical axes are JK, HI, and that tangent at N. It would have to be that tangent at N because it passes through point now. So I'm going to write out the proof of this, but that's the informal idea. So if we use power of a point a bunch of times, we have MK times MJ is equal to MI times MH. And then MI times MH is equal to MN squared if we use power of a point on omega. And so basically that means that MN has to be tangent to this circle of JLKN, which I haven't drawn. So MN, it has to be tangent to both this circle and omega, and so it's a common tangent of both of them, and so that means that those 2 circles have to be tangent, which is what we're trying to prove. So I'm going to draw that circle just for fun. Let's see. And we indeed see that the 2 are tangent at point N, which is pretty cool. So this problem, I would say it was categorized pretty correctly, about a medium difficulty IMO problem. And it shows an interesting way to prove that 2 circles are tangent, which is always pretty tricky in my opinion, especially if you don't know what the point of tangency is in the beginning. So if you like this video, give it a thumbs up. And if you'd like to see more like this, feel free to subscribe to my channel. Thanks, everyone.